Hi everybody, this is our lecture on section 6.4, which is on Green's theorem. So Green's theorem, it's only for 2 dimensions. So given a 2-dimensional vector field F, so it's Pxy, Qxy, and what's known as a simple closed curve C oriented in the counterclockwise direction. Excuse me. We get, so a simple closed curve C, so that's a curve that doesn't intersect itself, no loop-the-loops or anything weird like that. Just a closed curve C, oriented, and when you have that, it essentially encloses a region where you have an inner region and an outer region. Get rid of that hump there. The inner and the outer region. So this is C. And then you also have this interior of C. Right? And since you have an interior and an exterior of C, just 2 regions, just the interior and the exterior, you have a well-defined counterclockwise direction. Right? It's roughly circular, in some sense. Right? So in the counterclockwise direction, we get Green's theorem is that the line integral over C of the vector field PQ dot dr is equal to the double integral over the interior of C Qx minus Py dA. So you can calculate the line integral over the boundary as the double integral of this quantity here over the interior of C. Okay, so let's take an example. Oh, and by the way, this is 0 when the vector field is conservative. Let's mention that. Qx minus Py equals 0 when the vector field is conservative. So Green's theorem is exactly for vector fields that are not conservative in 2 dimensions. Right? Because when the vector field is conservative, the fundamental theorem of calculus tells us that the line integral over a closed curve for a conservative vector field is 0. Right? Which is what Green's theorem is telling us as well, because then it's just the double integral of 0 dA, which is just 0. Okay, no matter what the region you're integrating over is. So this is for non-conservative vector fields. For example, so let's let the vector field be equal to y squared minus x squared y and xy squared. So this is the p and this is the q, and this is not conservative because qx is equal to y squared and py is equal to 2y minus x squared, right? So now let's calculate both of these integrals. Let's calculate this double integral, and let's calculate this. Oh, I'm sorry, and I need to tell you what c is. And then let c be the following.
I'm with Dad.
And c is the following curve. So we'll take the line segment that goes from 0, 0 out to 2, 0, and this line right here and this circle. So this is the point square root 2, square root 2, and then this is the boundary of the circle. So this curve here oriented in the counterclockwise direction. So this is the circle of radius 2, and this is the line y equals x. So that's 1/8 of the circle, a 1/8 wedge of the circle. All right. So we're going to calculate both integrals. We're going to calculate the line integral over c, and we're also going to calculate this double integral. So let's do the double integral first. So the double integral of qx minus py dA is equal to over the interior of c. All right, so this is the curve c. Well, the interior of c is 0 as a polar region, 0 less than r less than 2, 0 less than theta less than pi over 4, right? As a polar region. So this is equal to the double integral. Well, first let's figure out what this is in terms of x and y over the interior of c. Qx, which is y squared, minus py So this is the double integral over the interior of c, x squared plus y squared minus 2y dA. So now calculating in terms of polar coordinates, it's the integral from 0 to 2 for r, and 0 to pi over 4 for theta. X squared plus y squared is r squared minus 2r sine of theta r dr d theta. Okay, so we took the integral, double integral for x and y and transformed it into an integral for r and theta. So this is equal to the integral from 0 to pi over 4, 0 to 2 for r to the third minus 2r squared sine of theta. So integral from 0 to pi over 4, r to the fourth, 1/4 r to the fourth minus 2/3 r to the third. Sine of theta from r equals 0 to r equals 2 d theta. So this is equal to the integral from 0 to pi over 4. So it's 16 over 4 is 4 minus at 2/16 sine of theta d theta. Antiderivative. Antiderivative is going to be 4 theta minus or plus 16/3 cosine of theta from 0 to pi over 4. So 4 theta, that's pi, plus, this is root 2 over 2, minus 1. Cosine of 0 being 1. So, right. Okay. So that's the answer. It's not a very meaningful number, but I mean you could approximate it if you wanted to. But that's the answer that we get. Okay. So now let's take a look at the calculation just doing the line integrals in terms of these 3 different parts of C. So, right, we've got these 3 different parts of C. The first part from here to here, so R1 of t, that's going to be equal to x equals t, y equals 0, 0 less than or equal to t, less than or equal to 2. And R1 prime is going to be equal to 1, 0. R2t, that's going to be equal to, well, that's a circle. So this is cosine t, or circle of radius 2 cosine t, 2 sine t, 0 less than or equal to t, less than or equal to pi over 4. And then R2 prime is going to be equal to minus 2 sine of t, 2 cosine of t. And then R3 of t is going to be equal to, well, that's the line y equals x. So that's t, 0 less than, well, actually this is going backwards, from root 2 bigger than or equal to t down to 0. Right? This is going from the larger value of t down to the smaller value of t equal to 0. And here R3 prime is equal to 1, 1. Okay, so the line integral, vector line integral over C of f dot dr is equal to the line integral over, well, the R1 part plus the R2 part plus the R3 part. Right, and what was f again? F was right here. Okay. So this is equal to, so for the R1 part, right, R1 is t comma 0, and then it's for t from 0 to 2, f at t comma 0, right, so the y is 0, so that's 0, and this is 0. So that's just 0, 0, r prime, whatever it is, dt. So that's just 0. Plus the integral from 0 to pi over 4 2 cosine t to sine t. So the x is cosine, the y is sine. So this becomes 4 cosine squared t plus, it's 4 sine squared t. Sine squared t minus 8 cosine squared t sine t, comma, x is 2 cosine, and this is 2 sine. So that's 8 cosine t sine squared t times r prime of t minus 2 sine t, 2 cosine t. Now let me stack these guys. dt plus the third bit, which was the integral. Well, it's the integral from square root 2 down to 0. But I want to flip that around. So you have to, instead of adding it, subtract it. So now going from 0 to square root of 2. So here, x is equal to t, y is equal to t. So this is t squared minus t to the third. And that's t to the third. Dot r prime is 1, 1 dt. Okay? This one is just 0. Right? Vector field is 0. So this is equal to 0 plus, so this one we multiply everything by sine. So that gives me minus 8 minus 8 sine to the third t plus 16 cosine squared sine squared plus 2 times cosine 16 cosine squared sine squared. Minus this one, so that's t squared minus t to the third plus t to the third. So that just becomes t squared from 0 to square root 2. So that's plus 16 cosine squared sine squared plus 16 cosine squared sine squared minus 8 sine to the third t. So we have the integral from 0 to pi over 4, 8 sine to the third t plus 32 cosine squared t sine squared t dt minus, well, this is 1/3 t to the third from 0 to root 2. So we get integral from 0 to pi over 4, 8 sine to the third t plus 32 cosine squared t sine squared t minus, so t to the third here So that's square root 8 over 3 minus 0. Okay, so let's go to Wolfram Alpha and plug that one in there and see what we get. So when we plug that in right here, this is the integral from 0 to pi over 4. 8 sine to the third plus 32 sine squared cosine squared dt gives us this answer here. 2/3 times 8 minus 5 root 2. So 2/3 8 minus 5 root 2 plus pi, right? Plus pi. And then minus root 8 over 3. So we'll need to simplify this. So 16/3 minus 10 root 2 over 3 plus pi minus root 8. And that's root 8 over 3 is 2 root 2 minus 2 root 2 over 3. So we get in the end 16/3 minus 8 root 2 over 3 plus pi. So I guess we need to look at that other one. Right, so that's what that one is as well, right? It's pi plus or minus 16/3 plus 8 root 2 over 8 root 2 over 3. Pi minus 16/3 plus 8 root 2 over 3. Oops, I have the plus and the minus mixed up, don't I? Minus 16/3 plus 8 root 2 over 3. So that was supposed to be minus 8. I lost my minus 8 and it became a plus 8. And so what you get is 2/3 5 root 2 minus 8. So this becomes negated. 5 root 2 minus 8 minus 2 root 2 over 3. So this is minus 16/3 plus that minus 2. So that's minus 16/3 plus 8 root 2 over 3 plus pi, which is the same answer as here. Pi minus 16/3 plus 8 root 2 over 3, same answer as below. Same answer as above. So one integral was definitely easier. I mean, the double integral was definitely easier than the line integral. There was a lot more going into it. And the reason for that it might usually be the case is because with the double integral, you're taking derivatives. So, I mean, hopefully it's going to simplify this function somewhat. So this might be more complex than this. In particular in the case of polynomials, right? Okay, so a few examples of Green's theorem there, or one example of Green's theorem calculated in two different ways. Here's an interesting connection between Green's theorem and areas. So consider the vector field. So that whirlpool vector field that we've been talking about. since the beginning of the chapter, minus y comma x. Right? In this case, qx, and it's not conservative, right? That's been our basic example of a non-conservative vector field. And in this one, qx minus py is equal to, well, qx is equal to 1. And then minus py is negative 1 equals 2. So, by Green's theorem, right, the line integral over C of that vector field, well, let's do 1/2 of that vector field, minus y comma x dot dr is equal to 1/2 double integral over the interior of C, qx minus py dA. So that's 1/2 double integral over the interior of C. And this quantity is 2. Bringing in the 1/2, that's equal to the double integral over the interior of C. Oops. Of 1 dA, and that is just the area of the interior of C. The area inside C. So, for example, if we had the circle of radius k centered, well, not just at the origin, anywhere. And oriented counterclockwise. So here's your x and y axis. Well, here's C. And that's the circle of radius k. And it's centered, somewhere at AB. Right? In this case, the line integral, 1/2 of the line integral over C of that special vector field, y minus yx dot dr, is just equal to, right, the area inside C. And that's equal to what? That's equal to k, or pi times the radius squared. Right? So that whirlpool vector field that we have been looking at, it's got some interesting, it's got some interesting properties to it, in that it just, relates to areas. I mean, it just gives you, by Green's theorem, the area inside C. All right. To finish out the section, I would like to go over the proof of Green's theorem. So, Green's theorem, again, is that the line integral, the vector line integral over the closed curve C, okay, is equal to the double integral over the interior of C, qx minus py dA. So the proof is long, but it's conceptually very interesting, and I wrote it out already so that we can go through it a little bit more quickly. First thing to do, okay, the first step is to, and this is a conceptually very nice proof. it's the one in the book. There's other books that have different proofs that are not nearly as nice as this one. So I don't know why everyone doesn't use this one, but here it is. So consider a rectangular region and its boundary curve split into 4 segments. So this is the rectangle. A less than or equal to x, less than or equal to b, c less than or equal to y, less than or equal to d. And then you can split the boundary curve into 4 segments. This segment, R1, this segment, R2, R3, R4. They don't have to be in order. It's fine. It doesn't have to be in order. Addition is commutative, and integration is summation. Right? That's why we use the skinny s for summation. And you can add up an integral over however you feel like splitting up the boundary. Boundary part 1, boundary part 2, boundary part 3, boundary part 4, all oriented in the counterclockwise direction. Well, R1 is t comma c for t equals a to t equals b. T equals a to t equals b. R2 is t comma d, so x coordinate t, y coordinate d, from t equals b down to t equals a. R3 is b comma t, from t equals c to t equals d. And R4 is a comma t, from t equals d down to t equals c. And R1 prime, R2 prime, R3 prime, R4 prime are real simple. 1, 0, 1, 0, 0, 1, 0, 1. Great. So let's use this other notation for the line integral. Right, this p dx plus q dy, it works out a little bit more nicely for this scenario. Well, it's the integral over boundary part R1, p dx q dy, boundary part R2, p dx q dy, boundary part R3, p dx q dy, boundary part R4, p dx q dy. Over R1 and R2, y is, the derivative of the y is 0. The derivative of the y is 0. So, q dy is 0 in both of these. And over R3 and R4, the dx is 0. So p dx is 0 in these. So, what do we get? So this is equal to the integral from a to b, p of tc, so that's the R1, dt. Right, dt is just 1. d of t is just 1. So it's integral from a to b, p of tc dt, minus the integral from a to b. So minus the integral from a to b of ptd, because this one's going backwards. The first one goes from a to b. This one's going from b down to a. So I want to flip it around. Right? But all I need to do to flip it around is just negate it. Right? I mean, the integral from a to b and the integral from b to a, they're just related by negation. So we take the integral from b to a, turn it into the integral from a to b, and it's just negated. Similarly over here, you get the integral from c to d of q bt dt minus the integral from c to d. You have to flip the d and the c around in this one. That's why you get the minus sign here. Q at dt. Great. All right. So that's the line integral. That's the line integral, and it equals this. Now let's look at the double integral of qx minus py. So over that rectangle R, the interior of that rectangular curve. Well, you just split that up into 2. It's minus the double integral over R of p of y plus the double integral of q of x. Right? It's a rectangle, so I can do the integral from a to b, c to d, py, dy, dx, plus the integral from c to d, a to b, qx, dx, dy. So I do the dy. Antiderivative of py with respect to y is p. So it's minus the integral from a to b of p from y equals c to y equals d. plus the integral from c to d of the antiderivative of q with respect to x, which is just q, from x equals a to x equals b. All right, the antiderivative of the partial derivative of q with respect to x is just, qxy. Well, okay, we're going from c to d, so that's the integral from a to b. P of d, right? P of xd, but that gets negated. Or sorry, this is negated, yeah. So P of x, y equals d, that one is, do I have them backwards? No, yeah, that one's negated because this one comes first, so it's negative pxd. And then minus pyc, minus again, or pxc, negative again, so it becomes positive. So it's integral from a to b, pxc dx, minus pxd dx, plus the integral from c to d, qby dy, minus integral from c to d, qay dy, but there's no need for x, you might as well call it t. There's no need for x, might as well call it t. No need for y, might as well call it t. Might as well call it t. These are the same four integrals as we have up here. So they're the same. All right, so Green's theorem is true for a rectangle. Okay, we're dealing with a lot more than rectangles, but so far it's true for a rectangle. Oops. So far it's true for a rectangle. Okay. What do we do after that? So consider a closed curve that encloses a stack of rectangles like this. So somehow you've stacked the rectangles together into one blob. Okay? So you got a bunch of rectangles, you've stacked them together in one blob. Rectangle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to rectangle 20 gazillion. However many rectangles you need. Alright, well, the double integral over and C is the boundary of this stack of rectangles. C is the boundary of this stack of rectangles. So the double integral over the whole rectangle, the whole stack of rectangles, is the double integral over the individual rectangles. Again, integration is summation. So I can integrate here, plus integrate here, 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 add them all together, and it's just the integral of the whole thing. So it's the double integral over all the individual rectangles of the it's the sum over all the individual rectangles, the double integral over the inside of the rectangles, qx minus py. But the first part of the proof was that Green's theorem works on rectangles. So the double integral over qx py over the minus py over the interior of R is the line integral over R itself. So now in this line integral over all these rectangles, this whole stack, right? Look at all the segments. The outer black segments are on one rectangle. The inner red segments are on two rectangles, in one direction in rectangle 5, the other direction in rectangle 4. Over here, it's up in rectangle 6, down in rectangle 7. Over here, it's up in rectangle 1, down in rectangle 3. Over here, it's left in rectangle 2, right on rectangle 1. So, the boundary over all the rectangles is just the sum of the line integrals over all those little segments. So it's the sum over the inner red segments, the line integral over the red segments, plus the sum of the outer black segments. Okay, but the sum over the inner red segments is 0. Because each inner red segment gets integrated twice. Left in one, right in the other. And they're just negatives of each other. Right, the integral here is 5. The integral there is negative 5. The integral here is pi over 26. The integral here is negative pi over 26. They just add up to 0. Plus the sum over the outer black segments of the line integral on the black segments. But the line integral on the black segments is just the line integral over the outer C. And that's it. Right, you splitting up the outer black boundary into these black segments. And then the red segments, they disappear. Step 3. Consider any closed curve C. Okay, so now we get to the full generality of Green's theorem. You've got a closed curve C. Okay, and you know, in the calculus that we're doing, these curves are like simple closed curves C. They're well behaved. They don't wiggle around too much. So there's a little bit of, this is not really a formal proof. It's just the idea of the proof. But it's fine because the formalities are sort of advanced beyond the scope of the course. But the intuition of the formalities is just what I'm telling you now. So that's the nice thing about this. The intuition came well before the formalities. Intuition came 200 years ago. The formalities came, I don't know, not much more than 100. Using a tight enough grid, you can approximate that C and its interior by a stack of rectangles. Right? So that grid has got like horizontal spaces, vertical spaces, horizontal spaces, x, delta x, horizontal spaces, delta y. And you can make delta x, delta y as tiny as you like. And the tinier it is, the better you can approximate C by this stack of rectangles and its boundary and its interior. Okay, so now the double integral over the interior of C. Well, I mean, if this stack of rectangles is super duper microscopic tight, right, the double integral over the interior is basically the double integral over the stack. Right, because the parts that you're missing are just so minuscule. So the double integral over the interior of C is the limit as delta x and delta y go to 0 over the stack approximation of the double integral. But the second part of the theorem was that Green's theorem works for rectangular stacks. So this is the limit as delta x and delta y go to 0 of the boundary of the stack approximation f dot dr. But again, the boundary of that stack approximation is so close. It gets so close to what C itself is. So as the limit is delta x and delta y go to 0, it actually is C. All right? Well, the integral over C. The stack is always the stack. It's never C itself. But it gets really, really, really close to C, as close as you would really like it to be. Okay, so that's Green's theorem, and that's pretty cool. This is these notions that we're talking about. These are notions of topology, which is a very interesting field of study, and it goes right into the proof of Green's. These ideas go right. I mean, they're very appealing, right? And that's the proof of Green's theorem. Okay, that's the end of the lecture for this section.